The story of the universe is filled with mysteries. But few are as transformative as the idea that black holes aren't silent. In the 1970s, Stephen Hawking made a discovery that really stunned the world of physics. He proposed that black holes are not eternal prisons, not perfect absorbers of matter and light, but objects that slowly evaporate. A prediction so bold that it forced scientists to rethink the origins of the universe, its future, and the hidden mechanisms that weave space and time together. Today, we journey into the heart of this idea, to understand how Hawking radiation works, why it matters, and how it might connect the death of black holes to the birth of entire universes. Most people imagine black holes as unstoppable gravitational monsters, swallowing everything in their path. But a black hole is far more complex. It isn't a physical object. It's a region of geometry, a place where space-time curves so dramatically that all possible paths lead inward. At the center lies the singularity, a point where our known laws of physics collapse. Around it is the event horizon, the boundary beyond which nothing returns. For decades, physicists believed that once something crossed this horizon, its information was lost forever. Black holes, they thought, were eternal. Hawking challenged that belief. To understand Hawking radiation, imagine zooming into the smallest scales of reality, the quantum world. Quantum mechanics tells us that the vacuum is never truly empty. Particles and antiparticles constantly flicker into existence, born from virtual energy fluctuations. Normally, these pairs annihilate each other instantly, but near the event horizon, the intense curvature of space-time can pull them apart. One particle falls inward, the other escapes outward and becomes real radiation. This outward-moving particle is Hawking radiation, and the inward-falling partner carries negative energy, reducing the total mass of the black hole. Meaning, every escaping particle is a tiny subtraction from the black hole's existence. This process is unimaginably slow, but relentless. Black holes are evaporating. The smaller the black hole, the faster it evaporates. A black hole the size of a mountain would release a burst of radiation so powerful it could outshine entire galaxies, right before vanishing. But supermassive black holes, like the one in the center of the Milky Way, take far longer. Their evaporation time is measured not in billions, but in 10 to the power of 64 years. By then, the universe will be dark and cold. Stars will have burned out, galaxies will have drifted apart, and black holes will be among the final luminous objects left. Their last moments, their final bursts of Hawking radiation, may echo across an empty universe. But evaporation introduces a deeper puzzle, one that shook physics to its core. Physics has a rule: information cannot be destroyed. Tear a book apart, burn it, dissolve it. In principle, every atom, every photon still carries clues to what it once was. But black holes seem to break this rule. If a black hole evaporates away entirely and radiates only random thermal particles, where does the information about everything it swallowed go? This conflict between quantum mechanics and general relativity became known as the black hole information paradox. And, solving this paradox led to one of the most profound ideas ever proposed in physics, the holographic principle. The idea that all the information falling into a black hole is stored on its surface, encoded in tiny quantum patterns on the event horizon. A two-dimensional representation of three-dimensional reality. In this view, black holes don't destroy information, they preserve it. And the universe itself might operate on similar principles. Now we step into the frontier, where cosmology becomes bold, creative, and honestly, deeply mathematical. Some physicists propose that the final stages of black hole evaporation could trigger new regions of space-time. In other words, the collapse of a star in one universe might create the initial expansion, the Big Bang, of another. Imagine a cosmic tree of ancestry parent universes giving birth to children through black holes. In this framework, Hawking radiation is not just a leak. It is the slow release of information that will pattern the next universe's structure. You could think of it as a kind of cosmic DNA. Others suggest that remnants of evaporated black holes, quantum seeds left behind, could actually grow into new universes with different physical laws, different particles, and, different destinies. The death of a black hole becomes the cradle of cosmic birth. If information survives inside Hawking radiation, then the universe may have a memory of stars, planets, atoms, basically everything that ever fell into black holes. This raises a really profound idea. Maybe new universes inherit information from older ones, not directly, but through fundamental constants, symmetries, and quantum rules. A universe that learns from previous generations would resemble a vast evolutionary system, with black holes acting as transitions between cosmic eras. This transforms black holes from destroyers into archivists, and, honestly, creators. Hawking radiation reshaped our understanding of black holes, but its true impact may be far greater. It connects gravity to quantum mechanics, links the smallest particles to the largest cosmic structures, and offers a bridge between the end of stars and the beginning of universes. It challenges the idea that black holes are silent endpoints and paints them instead as active players in the life cycle of the cosmos. Ultimately, this theory asks us to view the universe not as a one-time event, but as a continuous, evolving tapestry, where death and creation are deeply intertwined. Which idea resonates with you the most? Do you see black holes as the universe's destroyers or its hidden creators? Let me know in the comments. This is Infinite Narratives. Subscribe for more cosmic mysteries.